Fatal accidents have haunted aviation, starting from the very first attempts of mankind made to get off the ground. But the number of accidents is steadily declining with each passing year, all thanks to the most essential information that can be collected and analyzed after an accident. But what allows us to save the data people paid so dearly for? How do those fragile chips remain intact after a monstrous, devastating impact of the accident? And what loads are the emergency onboard recorders capable of withstanding? The world's first plane crash happened to be that of the pioneer Wright brothers aircraft in 1908, and it became the starting point in the history of aviation accidents investigation. Back then, the brothers managed to establish the cause of the accident and did everything to avoid its reoccurrence.
The sole purpose of such investigation, which is written down in all the fundamental documents of the International Civil Aviation Organization, is the prevention of future aviation accidents. That's what investigation procedures are carried out for. Even the establishment of the cause is, well, secondary actually. The most important thing that needs to be done is to ensure these accidents do not recur.
As a result of the IL-114 crash investigation in 1999, changes were made to the yaw rudder design on this model. The IL-86 accident in 2005 resulted in a change in the tail fin stabilizer control switch. After the findings of the Interstate Aviation Committee were acquired, Boeing changed the design of the nose landing gear on their 757 model. All these improvements were only made possible thanks to the information kept on the onboard recorders, the so-called black boxes. An onboard recorder consists of two modules: a recorder that collects and processes information coming from various aircraft systems, and a crash survivable memory module that stores all of the information. Exclusive standards are applied to the production of the crash survivable memory modules. Nowadays, they're made on high-precision CNC machines. The armored case can withstand loads of up to 3,000 Gs, but the exposure to high temperature can be much more dangerous to the microchips inside. Therefore, one of the most important elements of any crash survivable memory module is the filler, which protects the electronics from the effects of fire. And that's what chemists from the Kursk Avia Optomatica plant greatly succeeded in. Galina Nikolaevna, how can this powder withstand such a powerful thermal impact?
This composite compound was designed specifically to protect the electronic module of the black box and made with highly effective chemicals that absorb heat of 2,000 joules of energy per gram.
So it's an endothermic reaction.
An endothermic reaction of heat absorption. We managed to obtain such a durable protection using a specially selected formula, composition and structure of the composite material.
You know, I have an idea for a non-conventional experiment. Let's see how this powder can protect not just one of the circuit cards you work with here, but a chicken egg. Let's just put it on the block, fill it up, take it to the test bench, and see if the egg becomes boiled after 10 minutes at 2012 degrees, or not.
Let's try that.
All right. Only the crash survivable memory modules undergo the fire test. It's no use burning the entire recorder, but these tests are really stringent. They must simulate the aviation fuel burning conditions in the event of an accident. This test usually lasts 1 hour, but eggs cook faster, so we limited ourselves to 10 minutes. Let's see if our egg made any progress. So, 10 minutes have passed. We're recovering the box. The metal is glowing. That means the temperature of its surface is quite high. Now we're going to cool it in the water and extract the subject of our investigation. We're trying to act fast to maintain experimental integrity, as our research subject is too delicate. And in real testing conditions, the onboard recorders spend additional 10 hours in a chamber at 500 degrees after an hour of fire exposure. Well, where do you place your bets? And what is the temperature on the inside?
140.
140. Well, that's enough time for proteins to coagulate, right? We tried to act as quickly as possible. Let's see. So, all in all, the egg is half done.
Yes.
So, the egg didn't become hard-boiled. 2012 degrees for 10 minutes. Certification testing of onboard recorders simulates the average amount of damage that a crash survivable memory module must withstand. And as practice shows, they often withstand much greater workloads. And it suits us because we like to carry out tests at the breaking point. So, we're going to test this crash survivable memory module. We'll drop it from a great height, but we would like to see that drop from the first-person perspective. We're going to use this type of action camera for shooting. But, as our filming experience shows, such cameras don't always survive the moment of impact, because they record information on the internal buffer first, and only then the data is recorded onto a memory card. And if the camera turns off on impact, the last few seconds of footage are going to be lost. So, we're going to take another camera, like this old but good High 8 standard camera, that records data on tape. And it records all of the incoming information on tape without delay. That means the moment of impact will be caught on tape. Well, the construction looks kind of plain, but it's sturdy enough. We came to a desolate region of the Moscow suburbs to the piloting zone, where helicopter pilots sharpen their skills. We've made this contrast mark in the snow, and now I'm going to call the helicopter pilots and ask them to lift our onboard recorder to a significant height and drop it. Well, I'm hoping it'll land right here, because otherwise we'll have to look for it all over this huge field. So, here is our construction. The cameras are all running, guys. We'll go up to a height that's appropriate for today's weather. Surprisingly, the VHS camera looks almost unaffected. It's off, however. The onboard recorder is entirely intact, but our action camera seems to be under this ice somewhere. And here's our action camera. The case is broken, but that's not the most important thing. The main point is for the information to survive. To evaluate the results of our experiment, we went to the Interstate Aviation Committee, to the laboratory where onboard recorders are unsealed and transcribed.
The memory chips inside are protected, firstly, by the external casing that protects the recorder from mechanical damage. Next comes a special material that prevents the heat from getting through.
The removal of protective powder from the memory module is carried out under the ventilation hood for safety reasons. Well, I can't seem to find any signs of damage on this circuit visually. That means we can read it off, right?
Well, granted, we conducted a visual examination before applying voltage to any memory modules, but this is not enough. We will also examine our memory module very carefully and meticulously under a digital microscope.
Let's finish with this then. Here, we have another video camera, and we need to try to get the tape out of it. Unfortunately, when the camera landed, the tape mechanism jammed the film inside. So now I have to open it in such a savage way. But I'm being careful enough, however, so as not to damage the film itself. So this is where we'll examine this memory module.
We're going to conduct a visual inspection under a 600 power digital microscope here. That means we'll find any cracks that are not visually noticeable.
The memory chip integrity check has several stages. First of all, the chip is visually inspected at high magnification. If investigators have even the slightest doubt, the chip will be examined in an X-ray machine, which uncovers the hidden damage. After the investigators made sure the chip is intact, they will conduct volt-ampere measurements, which will finally allow them to dispel all doubts and work with the electronic chip freely. When the memory module sustains serious damage, the printed circuit board may be destroyed, but this doesn't stop the investigators. In such a case, the memory chips are extracted on the soldering stand and individually read off using adapters. However, we didn't have to do that in our case. So, Alexander, can we read this chip off?
Yes, we didn't find any problems in the course of both the visual inspection and the volt-ampere characteristics measurements. Moreover, we performed an X-ray examination and proved that everything was unaffected, not at all damaged. One more time. Well, in this case, the manufacturer also provides some kind of interface equipment, an adapter we can connect this chip to, and then we'll connect it to a computer using a conventional USB cable.
Ah, so this is a standard USB connector.
Yes, after all parametric information is read off, we use special software to process the flight information, and this useful flight information will end up looking like this. These are just the graphs of the flight parameters changes.
Specialists of different specializations analyze this data. Some evaluate the flight dynamics, others are analyzing the power unit, electrical and hydraulic systems. Special attention is paid to deciphering the voice conversations of the pilots. Reading the onboard recorders off is the starting point in the complete reconstruction of the aircraft's last flight. So our camera, the one that fell from a height of several hundred meters, has a memory card. The camera itself is not damaged. Can we see what is on this card and, if possible, restore the information?
Yeah, sure. First, let's try to see what a computer with a regular operating system shows us.
So, the card reads?
Yes, the card was identified. Here we have one file. Let's skip right to the end.
And here comes the fall?
This is the free fall, apparently.
This is exactly what I was afraid of. At the point of land impact, the camera didn't record the data onto its memory card from the buffer. But can you really try to restore such information?
In such cases, we always read the full binary image of the memory card off and then apply special methods of heuristic analysis in order to specifically establish where the information flow became interrupted.
Well, Alexander, while the memory card data transcription is in progress, let's go back to our cassette tape again. Well, it's plain to see that this cassette is okay. It survived. And we just need to put it out for digital remastering. But what about those recorders that use tape? Do you still get to work with them?
Yes, of course.
How do you perform such recorder's data recovery process after the accident?
If the tape becomes deformed under the influence of some sort of long-term thermal exposure, furrows may be formed on its surface. And if we put such a tape into a regular tape recorder, the distance between the magnetic head and the surface of the magnetic tape itself will constantly be altering. Because of that, the magnetic head will give us false or faulty information. In such cases, we use the magnetic optical research method.
The magnetic recording on the tape can be visualized. It is sprayed with an aerosol spray containing nanoparticles, which are deposited on the magnetized spot of the tape, making them noticeable. Then the images received are processed by the program and translated into binary code, suitable for decoding. We didn't have to go through all this trouble with our cassette. It was easily digitized and converted into a modern video format, but the recording is interrupted a few seconds before the landing. We couldn't determine the cause of this, but to our surprise, after reading the data from the memory card, the scientists from IAC Laboratory managed to restore the footage of the last seconds of the flight and the moment of land impact. Up next, the most extreme onboard recorder test. Will the fragile flash drive survive a cumulative charge explosion? Now we're going to get ready for another extreme test. We're going to find out if an onboard recorder can withstand the blast of a cumulative charge. We have the most common type of flash drive here. However, we've covered it with epoxy resin beforehand. We have the case of a crash survivable black box, and the composition such boxes are filled with. Its formula is kept low-key, but they still gave us a bit of it in private. I honestly don't know if it's toxic or not, so I'll use some personal protective gear anyway. Now I'm going to put our flash drive inside. Push it a little deeper so it's completely covered by the protective powder. And I keep pouring it. This is a rather dusty process, but I think the result is going to be interesting. So, the recorder became significantly heavier, and now we're going to take it with us to the Engineering Corps training range. We've arrived at the Combat Effectiveness Testing Site of the Engineering Corps Training Facility number 66. And this is where we're going to conduct the most extreme tests that have ever been conducted with onboard recorders. Mikhail, good afternoon.
Good afternoon, Alexander. Welcome to our training ground.
Well, as a matter of fact, this is the onboard recorder that we would like to try to perforate with a cumulative charge.
Can I see it?
Yes, it's this rather heavy little box.
Yes, it sure is. But the load it has to withstand at the moment of collision is probably quite heavy too.
Mikhail, about the cumulative charges, most people think that they are used to destroy armored vehicles, but what do engineering corps need them for?
You see, engineering corps mainly use cumulative charges to destroy fortifications and break through the concrete blocks. In fact, our most powerful charges can break through several yards of concrete. I think this charge will be quite enough for shooting today.
What is this? It looks like shell.
TS-1, trench shell, designed to excavate individual trenches in frozen or hard ground.
But before we test our box, can we actually see the engineering corps using these? Perhaps.
Yes, sure.
The trench shell consists of two parts. At the base, there is a cumulative charge. It's supposed to pierce the hard ground at a depth of 1.5 to 2 yards. The second part is the blast charge, which blows up after it's been embedded by the jet propulsion and throws the soil out to the surface. It takes about 15 minutes for a soldier to make a trench. That's enough to create a secure firing point. Shall we move on to the crash survivable memory module testing?
After you.
So, we have everything ready for the experiment.
We will only use the cumulative part of the shell to show the effect of the cumulative jet on the box, that is, and see what happens. Don't pull the handle out. That's it. Raise your hand.
Ready?
Fire.
Okay. Whoa.
Well, basically,
The second box just disappeared. And this is what happened to the crash survivable memory module. Well, this is just horrible. Look what happened to that thick cast plate. Okay, I mean, there is just the hole that is an 1.5 inches in diameter.
notice how it didn't just break through your experimental box, but also pierced one wheel here and another one.
Another wheel,
And
and there's a hole in the armor too.
yes,
Well, it's no wonder the onboard recorder is totally smashed and destroyed. Okay, to be honest, I'm just stunned to break through from such a distance. Let's see, to pierce 1.5 inches of metal, one wheel, another wheel, and the armor of this PTS from more than a yard away. To assess the level of damage, we're going back to the Interstate Aviation Committee laboratory. Since we did not use any special onboard recorders in our experiment, we have a regular flash drive. We will examine the aftermath of this experiment on our own. So, here we have the recorder we experimented on. This is the entry hole, and this is the outer casing. It flinched, and now the edges look like petals of a tulip. This is the exit hole inside the box. Now I'm going to remove the powder in the laboratory hood and see if the flash drive still has the information I've recorded on it before. So here is the moment of truth. This flash drive survived the blast of the jet charge that directly hit the box it was in. And visually, I don't see any signs of damage on it. Whether the layer of epoxy resin we covered it with helped or the jet blast was just too far away from it, I don't know. The only way to find out is to insert it. So, the light's glowing. Looks like our little flash drive is active. File management system. Well, there you go. There's the file. Oh no, it's working. It's working. We didn't really expect this result in the end ourselves, but the fact that a regular flash drive, which was a mere 6 inches away from a jet-charged blast, sustained no damage and preserved the data is not some kind of science fiction. It's the result of the work of chemists and engineers. Statistically, air transport is considered to be the safest one of all, though at this point, unfortunately, it's too early to call it 100% reliable. Nevertheless, there has been a steady downward trend of air crashes in the last 40 years. And the credit for this, without a doubt, goes to the engineers who provide the flight data safety and the investigators who establish the causes of accidents.